So the lab we're doing today is just to investigate the relationship between static friction and normal force. Okay, the relationship between static friction and normal force. So those two forces. Okay, we're also going to use that relationship to determine mathematically the coefficient of friction between our friction sleds and the floor. Okay, so these are our friction sleds. All right, Mr. Dickey and I turned these blocks into friction sleds using the handyman's secret weapon, duct tape. Okay, if you don't know to what I am referring when I say the handyman's secret weapon, you need, as a Canadian, to watch the red-green shows somewhere because, well, it's iconic. Okay, if the women don't find you handsome, they should at least find you handy. That was his motto, and duct tape was his secret weapon. So, okay. This is what we're going to be using, and we're going to be finding the coefficient of friction between the friction sled, the bottom of this block, and the floor. All right, so basically what we'll be doing is a series of trials where we are going to put different amounts of mass in the block and then pull it and measure the force that it requires to get it moving. Okay, now to get it moving, that's why this lab is about static friction. Okay, we're going to pull on this thing, slowly increasing the amount of force until the block starts to move. Then that trial is over, okay? Because once it starts to move, we have exerted enough force to overcome friction, okay? Overcome static friction. Once it starts to slide, it's kinetic. We don't need to worry about that, okay? So the data here is actually quite simple. You're going to have this force sensor, okay, which is a little different than the ones we've been using, and you're just going to hook it to the string that's on the friction sled. All right, so they look like this. You'll hook them here, and then there's holes for your fingers. Okay, so you'll have this on the floor. Okay, and you'll pull just ever increasingly harder until it starts to slide. Okay, then all you have to do when you get to your data is look for the largest number that you got. That largest number was the maximum amount of force you exerted before the cart started to move. Everyone okay with that? Okay, so that's all we need these for, is just to get the maximum value. If that number is negative, okay, that's fine. Sometimes these things go wonky, and instead of reading the force as being positive, they read the force as being negative. We're just looking for the biggest number, all right, within the data, because that's what we want. Okay, that'll be our force of static friction on each trial. Okay, so each trial will have a different amount of mass in here. When I alter the amount of mass in here, what force am I manipulating? I am manipulating F normal. Angela, can you just open that for me? Okay, so I'm changing the normal force by increasing the mass of this, because if I increase the mass of this, I increase the weight of this, which increases the normal force. Okay, now why are we doing this on the floor and not on top of the desk? Desks, well, the desks are more slippery, so it's harder to get good data, but the desks are also not, they're not level. Okay, they do have a slight incline. We don't want to be bringing that into our data here, so the floor is better. Okay. All right, so for our variables here, okay, remember we need a manipulated variable, which we kind of talked about, responding variable, which we also kind of talked about. They're the two things we're measuring, okay, and then we need 3 controlled variables. Now, one of these is crucial, okay? One of the controlled variables in this lab is actually something we're looking for in this lab. Okay, and so we need to make sure that that stays constant. Now, in order to control a lot of the variables that are going on here, okay, we need to make sure that the surface we use is the same. Now, we can, say, all right, I'm going to assume that all parts of the floor are equally clean/dirty, but is that a safe assumption? What should I do before I start this lab? Yeah, I'm going to need to clean the parts of the floor I'm going to use. All right, we're going to be doing a number of different trials here. I would suggest you use a different tile for each trial. Okay, and I would suggest that before you start, you go and get a paper towel from the bathroom, wet it a little bit, and clean the floor. Have another one to dry it. Okay, just so that you've got the floor being consistent, because there's something about the floor in the cart that needs to be the same, okay, for every trial. Why can't I just go over the same spot? Why can't I use the same tile every time? Yeah, there could be debris that comes off the bottom of the sled, okay? And each time you pull the sled, if even though you've cleaned the floor, is it possible that you scrape the floor even cleaner? Yes, okay, that's why we want to use, and assume, we're going to have to assume that all the tiles are basically the same. They are, okay, but we need to make sure that we're not using exactly the same space, that the conditions are at least the same. All right, so that's for your design. Remember, you need three controlled variables, okay, responding variable, manipulated variable, all explained. Okay, marked a few of the labs already, and I had to write in capital letters as a comment on several of them beside the variables, explain. Okay, you can't just say the manipulated variable is this. Okay, and you can't say it's this because it could affect this, or because it could affect the experiment. Lots of things could affect the experiment. How is it going to affect the experiment? Okay, we got to have detail here. All right, for our hypothesis, okay, so our hypothesis needs to talk about the relationship between force of static friction and normal force. That's the if part. Okay, so the relationship here, okay, that's the if part. The and part describes the experiment, same as it always does. Okay, then has to talk about how you will calculate the coefficient of friction, so mu, how you're going to calculate mu from a graph of normal force versus friction. Okay, you will be building a graph of normal force versus friction in Google Sheets. Okay, and you're going to need to be able to tell me how you can get the coefficient of friction from that graph. Okay. All right, so we've already kind of talked about the procedure here. Okay, we're going to have the wooden block. We're going to be pulling it with the force sensor. Okay, you're still going to use the air link things, connect to your phone, same as you always do. Okay, it's just this time instead of hitting the position thing, you're going to hit force. It'll say force pull positive, force push positive, and it should be pull positive. If it comes up with negative numbers again, don't worry about it. Just pick the biggest number, and that's your force. Okay, what you should see, okay, on the graph that your phone shows is you should see like this, and then all of a sudden it'll drop. All right, it should look like that. All right, you're going to want to obviously look at the data chart, okay, in order to do this. So you'll pick, all right, here was my maximum force of static friction value. Okay, so that would be, I don't know, we'll just say it's 10 newtons. I don't know what it'll come out to, but let's say 10 newtons. So that would be trial 1. Trial 2, be a different number. Trial 3, then you're going to build a graph after that, okay, that'll have normal force and friction on it, okay, and we just want to see the relationship there. What happens to the force of friction as normal force increases, and then calculate mu from that graph. Okay. All right, so, oh, there I did it again. So the graph you have looks like this. You're going to have the mass, and then the normal force. Actually, I think I took mass out, didn't I? It's still in there. Okay, so mass, then normal force, and then the maximum static friction. How do you calculate normal force in this situation? Mass times gravity. It's a level floor. Okay, so that's an easy calculation. This is your biggest number in your chart for each trial. Okay, then you will graph these two things together. Okay, now all I want to see for the analysis is the graph, and then I want to see your calculation using the graph, okay, of mu. I do not, I repeat, do not want to see 5 calculations of this. Okay, I do not want to see you calculate mu by going force of friction over normal force 5 times and then averaging it. Use the graph to get mu. Okay, I say that because even though I say it 3 times every lab, a third of people will do it this way. And then I can say, no, I explicitly said, do not calculate mu by doing this 5 times. Okay, use the graph to get mu. All right, then I want a little bit of a justification. So a couple of sentences explaining why what you did is calculating mu, okay, and little explanation to how you figured that out. All right, that's your analysis. So a couple of sentences and that single calculation, that's it. Okay. Then you got your conclusion, so copy paste your hypothesis and then explain why what you did here fits with your hypothesis or doesn't fit. Okay, sources of error, right? 2 of them with ways to fix them. And you don't have to worry about the class discussion. We'll talk about that. Actually, we've already talked about most of those anyway. Okay, everybody with me on what we're doing? Okay, so realistically, the procedure here should take 5 minutes. You really should be able to get pretty much the whole lab report done in class today. Okay. All right, I will stop talking so that you have time. Okay, questions?
Is there a set amount of weight you use for second?
Sorry, good question. So there's 5 trials, but you'll notice there's 6 masses. First trial, empty block. Second trial, put the 2 small ones in at the same time. Okay, and then go up one at a time after that. It's just these ones are so small. Like if you just put in the 5 gram, it doesn't make any difference. Like it's not heavy enough to make a difference. So put the first 2 in, then the others.
What's the mass of a block?
It's on here. 0.254, I think it was, right? Yeah, 0.254 kilograms is the mass of the block, empty. Okay, you add on whatever you put in, and it's engraved on them. So there's a 10, a 20, a 30, a 40, a 50, and a 1. Russ? Mass of block plus, each time. Okay, total mass. Any other questions? Okay, get to it. Somebody can use that one. They got to get an air link though.